Hi, my name is Julia Silge, and I'm a data scientist and software engineer at Posit. And today we're going to use this week's Tidy Tuesday dataset on GPT detectors. So these models that are trained to detect the output from large language models like GPT-3 and GPT-4. We're going to use this dataset about the output from these models to explore classification metrics. So these models are examples of binary classification models where you put in a text, a document, and then it gives you out a prediction. What it gives you out is a prediction that that text was generated by AI, by one of these GPT models. There are different kinds of predictions you can get out from models. The two that we're going to talk about today are predicted probabilities and predicted classes. So the first one is a number, a probability, and the second one is a class, like human versus AI. This data set comes from a paper that was written recently. It's a preprint right now that shows how these models do a worse job with human text written by human beings who are not native English speakers or writers. So what we can do with these different kinds of metrics, the ones that use probabilities, the ones that use the class, we can look at report performance overall, and then we can report performance in different categories and see which kinds of metrics work for these specific kinds of categories. Let's get started.
All right, let's look at these GPT detectors. So I am going to load the tidyverse, and then I'm going to load straight from the original package that Simon Couch put together with this data. And if I load this and then I look at data, I have it here. I'm going to get it from there so that things are set up right away for me to use. So each one of these rows is a document, and the document was either written by a person or generated by one of these GPT GPT models here. And so when it is generated by one of these large language models, it gives us the prompt here, what prompt it used, and then we have which model. So if we look here, we can count by model. So there are, not model, detector. So the model is what generates it. So you can see they use GPT-3, GPT-3.4, GPT-4, and then also people, real documents. The detectors are the models that have been trained to detect whether it is written by one of these large language models or not. So you can see we have slightly different numbers, but many of these documents are submitted to many of the detectors. So there's, these aren't, each row is not a separate document because they are sent to multiple models here. What else do we have? Okay, so kind is it real, or is it one of these AI models? And then we have two columns that I want to focus on here. The pred AI is a probability. It's a probability that this detector thinks this document is generated by an AI. So here, this one is high, this one is low. And then the predicted class is instead of a predicted probability, is it an AI or is it a person? So you can see here when the predicted probability is low, then we think it is a person. When the predicted probability here is high, this detector thinks this one is in fact an AI. So we're going to talk about metrics for these kinds of classification models, and we're going to talk about what kind of metrics use probabilities and what kind of metrics use classes. Some models only give you the class. Some types of models are not, the way the algorithm works, they are not actually able to give you a predicted probability, or some of the implementations of certain models are set up that way. So it's good to understand these two different kinds of predictions and how we can use them when we're evaluating models. So let's do just a real brief bit of exploration. First of all, let's see how these things are, line up. So the paper that this came from was interested in the issue of native English writers compared to non-native English writers. So that's in this column. And notice that when it is NA, that is when it is made by an AI generated by one of these models here. So let's see how this breaks out. So if you are yes or no on being a native English writer, then you are really a human. If this value is NA, then you are really an AI document. And so then here we see the predicted class. So some of the real AI documents are predicted to be made by an AI, and some of the real AI documents are predicted to have been by a person. You can see actually more than here, so not doing so good over there. And then we can compare this. This is like a like how we make the predictions for humans that are native speakers. These are how we make the predictions for humans that are non-native speakers and writers. So that's what we've got here. Let's do another little bit of a exploratory visualization here. So let's filter down to just the people. So the native and non-native English speakers. So let's not look at the AI documents right now. And let's put the predicted probability on the x-axis. Let's color by this variable. Let's do a geom histogram. I don't know. I mean, the default's probably fine. And let's say show legend equals false, because I'm gonna facet wrap here. So I'll say native like this. Let's see how this looks. Okay. Whoa, that is so dramatic. Let's this will be a little bit easier to see if we put it more like this, I think. And let me just zoom in here. Whoops, that's what I meant to do. Okay. Okay, so on the top are let's start at the bottom. On the bottom are the native English speakers and writers. And this, remember, is the predicted probability that that document was made by an AI. So this looks, I guess we would say, good, quite good, right? Like we have many of these documents are predicted to have a low probability of being generated by AI. Now, the situation is really different when we go to the non-native English writers. In fact, more are predicted with a very high probability to be AI than be made by human. So these two distributions are hugely different. If we want, we could, let's make n call equals 1. If we take this out, we can see the distribution for also for the real AI thing. So on the bottom, AI documents. On the middle, real humans who are native speakers. On the top, real humans who are not native English writers. So this distribution is pretty different, right? And like the distribution for non-native English writers looks more like the distribution for AI generated documents. It's actually worse though, because the ones on the bottom are AI and the ones on the top aren't. Okay, so that's what this paper is about here. So what we did here is we looked at the distribution of the predicted probability. And that's a great thing to do, right, to make these kind of visualizations. But what we want to do is walk through how we use metrics to measure these kinds of differences. So I'm going to use tidy models for this, but I'm not going to build a model. Instead, I'm only going to evaluate a model. So the package that in tidy models is used for evaluating models, measuring how they're doing, is called Yardstick here. So I'm going to load Yardstick, and then I'm going to show how do we go about computing some of these metrics. So a lot of the metrics, shocking amount, are based on a confusion matrix. So if a confusion matrix uses a predicted class, so that is this thing here, predicted class. Sometimes this is called a hard class prediction. So if we put predicted class here, we will see how we can see a little 2x2 matrix or table that tells us how the model got things right and wrong. So over on the horizontal side is the prediction, and the vertical side is the truth. So let's read down in human. When it's really human, 2019 of those are predicted to be human. 449 of those are predicted to be AI. If we read down from truth in the AI, we see 1,158 are predicted to be AI, but a lot more, 2,559, are predicted to have come from human. So it looks like it would, just by looking at this, what I would say is it has an easier time with the human class than the AI class. It's easier to tell here that a human document is generated by humans than an AI document is generated by AI. But we can combine like these. There's like 4 numbers here, but they get combined in all kinds of ways to compute all kinds of like different takes on how a model is right or wrong. So, also, if you want to look at this, we can make a little visualization here by piping this to autoplot here. And we can see this visually, which sometimes is, unshockingly, much easier. So we can see in the data set, there were more AI documents than human documents. And we can see that the human documents were predicted correctly way more than the AI ones. Okay, so let's talk about starting to compute some of these metrics. Probably for these kinds of classification models, the things you probably hear about most are the one thing is accuracy. So accuracy is just plain old the proportion of the data that is predicted correctly. So let's say we do the same thing here, kind, class. So remember, this is the true label, this is the predicted label, like this. So this gives us an accuracy. Accuracy is a number that goes between 0 and 1. 0 is bad, 1 is perfect. 0.5 is random guessing, at least for a binary model like this, which is like a yes-no kind of thing. So overall, aggregated over all of the detectors, all of the documents that are in here, the accuracy is not that much better than random guessing. So that's kind of some useful thing to know to start with. But we can also compute these. Across different categories. So let's see. What am I doing? Let me get rid of that. Let's copy this, and then we can just add a group by statement like you may be familiar with from dflyer. So let's group by detector and see, do some of these models do better than others with a just big overall aggregated number? Moderately, right? Like this one is best. This one is worst. This one is actually worse than random guessing, by being under 0.5. So I don't know. Yeah, there are some differences here. And we can see that by computing this metric across groups. So what happens if we do it across the variable native, which is about whether it's a native English writer or not. So so keep in mind what these differences are, right? Right around 0.5. Look here. Huge differences. So for native English speakers, the accuracy is very high. So good. This is like super, super good. The accuracy for non-native English speakers / writers is so much worse, so much worse. And in fact, it is even worse for the AI generated text. So native NA here, remember this means just for the AI generated text that come from Chat GPT, or not Chat GPT 3 or 4. Okay, so this is a metric that uses a predicted class, and we can look at it across groups. Now you probably, if you have learned a little bit about machine learning, you've probably heard about how accuracy is not always a great option. It's especially not a great option if you have class imbalance. We don't have huge class imbalance here, so that might not be as concerned, but it is true that accuracy gives you one number that tells you how much of your data you predicted right and does not tell you much about things you might be interested in, like the true positive rate or true negative rate. So because if you remember from this confusion matrix, the model can be wrong in different ways. And it can be more wrong in one way than it is wrong in another way, and that affects how a model behaves in real life. And you may have, in a real application, one of these things would be much worse than the other. I would say identifying an AI or identifying a human text as AI is probably way worse in these applications than identifying an AI text as human. This probably looks about right for most ways people might use this, but still we can get better estimates of how this works. Okay, let's talk about sensitivity, which is the true positive rate. So I'll just copy this. So just like we did before, we can compute the sensitivity for the data set as a whole. So this is also a number that goes between 0 and 1, where 0 is bad, 1 is good. This is the true positive rate. This looks, maybe not awesome, but what happens if we do it across the different detectors, the different models that are made to find this kind of text? We see some variation here in the true positive rate. One is better at this, one is worse at this. What happens if we try to now do this across the different kinds of this variable about native speaker versus not? Oh boy, we got a warning message. Okay, so what is going on here? We have an NA for these categories. So for this is the real humans, and this is the AI generated documents here. So we can compute it we can compute the true positive rate for the AI generated text, but we cannot compute it for the humans. And this warning tells us why. There were the true positives plus the false negatives were 0. There are no, let me make sure I can try to say this right. There are no AI generated documents written by native English speakers or non-native English speakers for that matter. So in those cases, we cannot compute the true positive rate. The true negative rate, which is the kind of flip of that, works the opposite way. So if I were to go here and I change this to specificity, which is the true negative rate, like this. Oh, that's across detector, right? So I can see what is the true negative rate. If I change this to native here, the same thing has happened, but it's flips. I cannot compute a true negative rate for only the AI generated text. I can, though, for the human text. And so I can look at the difference. And again, we see here for native English speakers, the true negative rate is great. It's very close to 1. This is a good thing. For people who are not native English speakers or writers, the true negative rate is pretty bad. And so we see that difference here, which remember is what the original paper is about. So the reason why we end up with these NA values here is because of the confusion matrix. So if we take this, let's just take this here. Here, look at the confusion matrix, and let's only look at the real humans. Is NA native, like this. And here, if we look at this confusion matrix, we see that all of the elements are over here in the truth equals human column, and there are zeros here. And because of these 0 elements in the confusion matrix, we get these NA values. We get these NA values here because there's a 0 there, and we can't add those together. You know, there's nothing there, and so we cannot compute what that means. Okay, so these were examples of metrics that use a predicted class. Now let's go on to talk about metrics that use a predicted probability. If we go back and look at our data, that's this column. So this is the predicted class, and this is the predicted probability. So one really common metric that uses a predicted probability is the ROC curve, or the area under the ROC curve. So let us compute an ROC curve. ROC curve. We will say kind, but now we will say predicted, not class, but AI. So we compute a curve like this. It does all the, all the aggregation there for us, and then we can make a visualization for it. So here is aggregated all together, all the different detectors, all the different kinds of documents here. Just overall, here is what the ROC curve looks like. I said before that the accuracy indicated it's like a little better than random guessing, and that's what this plot kind of looks like to me as well. The diagonal line is the line of random guessing. Now I can make ROC curves for something in my data, like some like disaggregate it by something I have, like say the detector model, the model that is built to detect AI generated text. So here, we see that some are going under the line. We kind of see these here. So what this tells us is how are the different models behaving? How are the different models behaving? And we can use here we have a visualization of what this looks like, but we can calculate those areas under the curve. So what we would do, let's take this and let us, instead of ROC curve, let's compute ROC area under the curve like this. So what we have here is the area under the curve, and you can see that here's that one that goes below that is that one, right? Yes. So this is the one that goes below the line. We see here the area under curve here. So here again, this is a value that 0 would be opposite. You were perfectly predicting opposite. 0.5 is random guessing, and 1 would be perfect predictions. So that's what how area under the curve works for RUC, AUC here. Let's go back here, up here, and let's see, can we do this for across the native variable? Like, can we make a ROC curve for the native English speakers versus not? No, we cannot. We cannot. So, and this error tells us why. There were no events in truth with event level AI. So this is saying there are no native English speakers who their true value is AI. Again, we're back to this. None of the native speakers we're AIs, and so some metrics we just can't compute across groups like this. Like we're not able to do that. So let's look at a different kind of metric that uses a predicted probability. Let's look at the mean log loss. So this is a metric that computes log loss, and the way that it works is again, zero is good, or not again, here zero is good, a small number is good, and a high number is bad. So log loss here takes into account the specific value of the prediction. So if the say you have two probabilities of 0.6 and 0.9, both of those you would say are a yes. They both are above 0.5, so they were yes. But the 0.9 is a there's a higher probability. It's like more certain. The model is more certain that one is a yes, and less certain here. And so log loss takes into account those differences. It's how right or wrong they are. So it's this issue of being more, how sure is the model? Let's penalize the model when it is less right or more wrong, and let's let them tell the model, use loss here to say when it is more right and less wrong, that's better. Okay, so we will do this. So we start right by just doing this overall mean log loss. It uses the same inputs as ROC curve here. So we can overall, we can do an overall value of the log loss. Remember, if this number is smaller, it's better. 0 would be perfect. So let us add in here, let's group by detector first. And so let's see how these different models do. Oh, this is a pretty big difference. So measured with log loss, this model is the best, and it is actually way better than this model. The mean log loss here is showing here across detectors a much different kind of results. And instead of doing this, we can see, are we able to do this across values that are only apply to one class? And the answer there is yes. And here we're able to see, again, measured in a different way, to look who's doing the best. Native English speakers. Native English speakers, the log loss is very low, at least compared to these other numbers. It's looking great. For non-native English speakers / writers, the log loss is quite a bit worse. But then for the AI generated text, it's even worse. So this kinds of, and of course, if we wanted, we could see across different, we can aggregate this in any way that we want to and see, oh, this detector does better than this one at the difference or whatever. Like we can like just continue to disaggregate these kinds of metrics to give you a better idea of how your model is performing.
All right, we did it. We didn't train a model, but we did use output from some models that are already out there, and we evaluated how the model performs in different situations. The specific kind of situation here is that a variable that we are interested in, the native versus non-native English writer status of human beings, only applies to one class. This happens in real life quite a bit, and so understanding how it is that we can go about measuring how a model does with different kinds of inputs, probabilities versus classes, and what are the options that are available to us depending on what we are interested in. So I hope this was helpful, and I'll see you next time.